Alright, let's finish this exercise once and for all. So, um, we have this function. Okay, so. Okay, this is really bad in terms of just calling like what things are we're using to refer to functions. Let me just see real quick. What did I do? Because I'm going to start by finishing up um, last time. Okay, so show that we can choose such an f so that this happens. Because what we're going to want to do is this f here. What we're going to want that to be g of f here. Where here. So what this is this should really be like f tilde maybe, or no, I've already used f. Okay, maybe f with the hat over it or with a caret. This is usually used for like you'll see this notation for like Fourier transforms, but since we're not there yet, I'm fine using this. So f hat, and we're going to let f hat equal g composed with f, where g is a function from b and f is a function from d. Okay, so yeah, the notation in this problem is a little confusing. I'm going to go through it in a way where I'm just going to take this function g composed with f. I'm going to call it h. So we can choose of such we can choose. So what we're going to do is we're going to prove there is a function h which maps from a to the closed interval from 0 to 1, which is equal to 1 on the set C. Okay, so first what we're going to do is let f be here. Let f tilde. No, let's use f hat here. Let f hat be any function from part D. We want to find a function f which satisfies the conditions from part D and also satisfies f is going to be greater than f of x is greater than or equal to epsilon for all x in the compact set C. Okay, so how are we going to do this? So we have f hat is any function from part D. Now since C is compact, f hat attains its minimum on C, i.e. there is some point C in the set C such that for every other point here, let's call this x. So there is some x in C such that for all points y in C, f hat of x is going to be less than or equal to f hat of y. Now, note that this isn't necessarily true in an open set because you can have a situation where, like, where as you get closer to the boundary of the open set, the function gets smaller and smaller and smaller, and in the limit it approaches some point, but you'll never attain that limit, because attaining that limit would only really be obtained on the boundary of the open set, which of course the boundary of an open set is not contained within the open set, because that's how open sets work. Okay, so anyways, we have this minimum being attained. Okay, so let Ooh, I should not have used x here. Let's call this y and see such that for all z, f of y is less than or equal to f of z. Okay. So y is the minimum point. So let f of x be defined to be epsilon, or here, let's do f of x. Hold on. My notation that I have in my notes is different from here. So f of x is going to be, we'll take f hat of x times epsilon and divide by f hat of y. Then for all z and c, what happens when you plug in f, when you evaluate f of z? Well, this is going to be f hat of z times epsilon over f hat of y. And so this is, so f hat of, we know since z is in c that f hat of y is less than or equal to f hat of z. So that means that this is going to be, since f hat of y is in the denominator here, we reverse the inequality and we get that this is equal to, or that this thing that we have on the left is greater than or equal to f hat of z times epsilon over f hat of z. Its minimum strictly greater than 0. That's actually important here, and I should have, yeah, it's good that I caught this, because you need the fact that f hat is strictly positive on C, because otherwise you're dividing by 0 here, potentially. If you choose, you want to ensure that if you choose any element z in C, that you're, what we want to prove, we need to ensure that f hat of y, so here, I'll put it there, i.e. there is a point such that f hat of y is strictly greater than 0, and it's strictly greater than 0 because f hat is strictly greater than 0 on the entire compact set, C, but it's also the minimum. And the fact that, so anyways, the fact that f hat is strictly positive means that we're not dividing by 0 here. So anyways, f hat of z times epsilon over f hat of z. And of course, now we've got f hat of z in the numerator and denominator, so that's just epsilon. So f of z is greater than or equal to epsilon for all z in C. Alright. See here. F is also C infinity because what we're doing to get f is you just take the C infinity function f hat and multiply by a constant, a positive constant. The positive constant being epsilon over f hat of y. So f is also C infinity. F is identically, f is strictly positive on C because it's greater than or equal to epsilon on C. So you could even write f is greater than or equal to epsilon, which is strictly greater than 0 on C. And f is identically equal to 0 outside of the closed set B from part D. And this is true because f hat is identically 0 outside of the set B. And so multiplying f hat by a positive constant won't change that. Okay. Thus, f satisfies the conditions of part D And furthermore, f is greater than or equal to epsilon on c, i.e. for every single x in c, f of x is greater than or equal to epsilon. Alright, so that's just wrapping up some stuff from last time that I guess we could have thrown into the previous video just for, to make sure that everything was there, because here, like, you had to, like, if you're watching this after taking a break from seeing the last part, you might have to remember, like, oh, what were we talking about in that last video? But anyways, this makes it better because we don't have that much left to do in this problem. Okay, so now let H be G of F, where G is as in part. Let's see here, what part did it come from? Where G is the function of part B. And this is also bad because in part C we also used a function G, and those functions G, or that function G, was used to define the function in part D. So there's just like I feel like Spivak just forgot that there's that, like, he was like, okay, he's like seeing the alphabet, he's seeing the ABCs, and he goes like F, G, and then he just stops singing because he doesn't realize that there's other letters in the alphabet that you can use besides F and G to refer to functions. But whatever. So G is as in part B, and we're taking H to be G composed with F. So now let's write out explicitly what we're going to claim, because we need to state all of these, or I want to state all of these things because it's very easy to forget and get messed up in all the details. And it's something that, the more exercises you do in math, the more details you're able to keep in your head at one time. It really helps you increase your mental RAM. So I claim that H maps from A to the closed interval from 0 to 1, and H maps from A to 0 to 1, H is C infinity, H is identically equal to 1 on C, and H is identically 0 outside of a closed, or the closed set B, where, just to remind you, C is contained in B, which is contained in A. Okay, so this is what we're claiming, is these 1, 2, 3, 4 things. Okay. H is C infinity, since G and F are. Okay, so there's one. Let's see here. Now, let's see here. Remember, F maps from A to the real numbers, and G maps from R to 0, 1. So, H maps from A to 0, 1. Now that I think about it, I don't really know if I was super careful when I defined F to make sure to specify that the domain of F is A. I may have just said like I may have used notation that made it seem like the domain of F could be all of Rn, but you could just define. The way we defined F is we defined F to be 0 outside of the closed set B, and so it doesn't really matter what happens outside of A. By my definition, if I had defined it on all of Rn, then it would just be 0 outside of A. So there's no real issue in just restricting the domain to A and keeping everything the same within A. It's just minor points there. But some people might be a little worried about being pedantic and stuff. But anyways, okay, so we know that H maps from A to 0, 1 because, well, you just sort of, A goes, so H goes from here to here to here. Well, H goes from here to here and then from here to here, so it really goes like there to there. But anyways, so that's two things out of the way. If x is in C, then f of x is greater than or equal to epsilon, which we just proved by our construction of epsilon. So h of x equals g applied to f of x. And since f of x is greater than or equal to epsilon, we know from part B that g will send that point to 1. So this equals 1. Okay, so that's 3 down, 1 to go. Since f is 0 outside of the set B used earlier, and that's of course the closed set B that we defined in part D, and since g of 0 equals 0, we know that h of x equals g of f of x equals g of 0 equals 0 for all x which is not in B. This completes the proof. Alright, and so there we go. We're done. We've provided a function which is so this is actually really neat. You take a because if you think about what we're actually doing here is you take an open set A here and you take a closed set C, which is inside here, or you take an open set A and you take a compact set C inside of A. And what I'm saying is that you can take a function which is C infinity, so it's super, super nice and continuous and smooth and everything. It has really nice properties. And this function is 0 outside of the set A. And then when you're in the region between A and C, this function starts to increase from 0 all the way up to 1. And then when you get to C, your 1 on the function evaluates to 1 in the entire region of C. And so you sort of have this sort of like plateau-like mountain that you can get here, where if you're plotting this function, it actually looks like you've got this like really flat surface on the set C, and then you have these cliffs that fall off, and you reach ground level on the boundary of A, and then you're just on the ground outside of A. So the existence of such a function is really nice. It's really important in, especially in real and functional analysis, and also in topology in general. Like I said, Munkres takes a lot of time to really appreciate this, the fact that this thing exists, and there's a lot of stuff you can do with measure theory about, like the existence of these types of functions are really useful in there's a lot of measure theory stuff that you can do with this. There's a lot of stuff. I seem to recall this coming up a lot when learning about Radon measures in Folland, if I'm remembering all the details correctly. And in fact, in Folland, they actually give a proof of Eurozone's lemma. They give a proof of this fact. The nice thing about that proof, though, is that it's like one paragraph. It's super short. It's super concise. If you look through Chapter 4 of Folland, you might be able to do, because Chapter 4 is just basic point set topology, and so you might be able to read through most of that, if not all of that, without reading the rest of the textbook. and it goes through point set topology sort of really quickly, so it may be not good for your first time, but it covers all the really important facts very quickly, which is really nice. You get to this fact, and it's just, the proof is just one paragraph, and it's really nice and clean and simple. Whereas here, it's nice that we've been able to get at this proof with not having that many sophisticated tools, but I feel like just the pure amount of time, because this, like, I've had like 5 videos, most are like around 20 minutes or so, so this is like probably, I don't know, I'm not good with numbers, probably over an hour of total video time. So this does take some, maybe it's just because like I like to go into a lot of details and do exactly what I'm doing right now, where I just sort of ramble on about stuff. But it is really neat that we're able to prove this theorem without using a lot of complicated machinery. It's just that it took a while. And maybe if you read through chapter 4 of Fallen, then you can get to this point, and just because of how much cleaner it is, it's a lot more concise, and it's sort of a nice. Well, I don't remember the proof itself being particularly nice. It's just very clean. There's not a lot of clutter. There's not a lot of details to go into. Well, there are details to go into. It's just that everything's been covered. All the tools that you really need to make the proof quick have been covered. Okay, so I'm going to stop rambling about this. But yeah, this is basically everything that you need to solve this exercise. Sorry if there's some details in here that are a little like especially that metric space stuff. There could be much easier, much faster ways to do it. Even using just the tools from this textbook that you've been given so far. But in any case, this is a proof of Urizone's lemma. And so we are done.